Hello, everyone. Thanks for attending this talk. My name is Shiva. I'm a senior software engineer in the Personalization Infrastructure team in Netflix. I'll be talking today about a Spark-based stratification library, which was built to cater to some of the machine learning use cases at Netflix. Here's the outline of my talk. I'll be starting off with giving you some background on how we do iterative ML in Netflix. I'll briefly talk about our offline ML library called Boson, which is used by several of our research teams, both in production as well as in the exploration phase. I'll deep dive a little bit into some specific use cases for data sampling, aka stratification. I tend to use the words sampling and stratification interchangeably in the presentation. And then I'll conclude the presentation with some concrete API examples of how we use the stratification library for. As most of you know, almost everything that you experience on the Netflix homepage is a highly personalized experience underpinned by several machine learning algorithms. In fact, we like to say that Netflix is not a single product. It's actually more than 100 million products, each of which is tailored to the unique tastes and interests of all our members. So to give you an example, there's a model that learns the ranking of the entire catalog of all the videos for each Netflix member. Similarly, there's another model that generates the rows and orders, that first selects the rows and then orders them according to what you have done in the past. So that's also personalized for you. Each title in our catalog has several candidate images that we can choose to show on the box art display. Even those are backed by machine learning algorithms. So needless to say, machine learning, the importance of machine learning for Netflix business cannot be overstated. Right? Over 80% of what our members watch comes from our recommendations. Our researchers continuously iterate on our ML algorithms and all its input features. Using historical data from our snapshot infrastructure, which I will refer to briefly later, we are able to rewind to an arbitrary point in the past and go back and check if a slightly different machine learning model or a slightly different set of features and data could have helped us predict some of the plays better. So we are able to do all of this offline without actually going to an A/B test. But once we have promising offline results, Netflix is a very data-driven company. We go to A/B test, we try all our new algorithms, and then use that data to then roll out to production. Here's a simplified view of the ML research pipeline that all our researchers go through. So you start off with a hypothesis. It could be a new machine learning trainer model or a new set of data that you're using to generate features. You start prototyping that idea, and then you analyze how that idea is doing offline. And usually, the prototype and analysis is a short loop that is done multiple times until a certain degree of confidence is reached about the hypothesis. And then once there is sufficient confidence, the researchers, there's a proposal to go to an A/B test to try that idea in the wild, and if it succeeds, hopefully profit, and then we productize. So what are the key requirements, right? So when we experiment offline, we have to iterate very quickly. And when we are ready to move to production, we have to take what we have in terms of the prototype code and some of the analysis tools that we have built, and the transition towards production must be smooth enough. And the two key technologies that allows us to make this transition quite smooth is one is Spark, because it's quick because of the distributed compute. We use Scala, runs in a JVM. That means it's compatible with all our online services that are all written in mostly in Java applications and are running as distributed microservices in AWS. We are also able to iterate very quickly using Scala in the offline phase because Scala is functional. It's easy to write code there. It's also very strongly typed, fewer chances of making mistakes, and so on. So Spark and Scala combination tends to be the sweet spot for almost all our researchers. I was alluding to the fact that the speed of iterations is very important in the offline experimentation, in the offline experimentation phase. And one of the things that enables it is a very shortened pipeline to try out new ideas. So we tend to use a lot of notebooks. In the offline phase, we do skip certain stages that are not really necessary in the overall pipeline. And while we do that and make some compromises there, it must be noted that the entire pipeline must be representative of what will be actually tested in the wild. For example, if you're using a huge data set to train and test in actual production, you have to make sure that in the offline phase, even if you're using a much downsample data to progress faster, the downsample data must be representative of the original data in terms of its distribution, in terms of some of the characteristics you're sort of cherry picking, training your model appropriately. And that's not just for model training, but also for evaluation data sets and so on. So, and most of my talk, the rest of my talk is really focused on how we downsample it, what sort of APIs are provided in our library, and how we enable our researchers to do arbitrary stratification on different kinds of data sets. Let me just take a brief detour and talk about Boson. So we have an offline machine learning library, which is codenamed Boson. Boson also exposes mostly a Scala and Spark API for all our ML use cases. It focuses on offline feature engineering and training for both ad hoc exploration as well as production use cases. So you write the same code using Boson, try it out in your notebook, and then you could copy paste all that code from your notebook to a GitHub repository and then have it deployed in production pipelines. Think of Boson as a sort of a subset of sklearn, but for the Scala and JVM ecosystem. I say subset, but there's also a lot of different components in Boson that are different from sklearn and are very Netflix specific. We have interfaces that connect to Netflix platform, to AWS and so on, which makes the life of all our researchers quite easy. The goal is to make sure that anything that's reusable across different research teams is housed in Boson so that our researchers can focus more on A/B tests and quick exploration rather than worrying about the infrastructure pieces. The core data abstraction in Boson is the Spark frame. All our data is typically stored in Hive or in S3 as Parquet files, and the most of the data is read into memory as a Spark data frame. So this is a sort of a zoomed in picture into the pipeline that I was briefly showing earlier. So on the left is our snapshots infrastructure. Incidentally, there is a parallel talk going on in room 3016 that's talking about the next generation snapshots infrastructure. So in the picture, I'm showing our snapshots 1.0 infrastructure, which is sort of a cron job that runs once a day, goes out and collects all the data about a subset of users, and we snapshot all the relevant data in S3. So in order to create that subset of data, we do some stratification and identify the right set of users to stratify that could be later fed to our model training phase. After we capture the facts, we store it in a common place that can be used by the feature generation for the machine learning models. To the right of snapshots infrastructure, that's the view that the machine learning researchers are typically involved in. So they start off with an experiment design, and for that experiment, you identify what your correct labeled data set is. Labeled data set is used to train supervised models, and starting from that, if your data is too big and you want to quickly iterate, there could be some stratification applied there. And once the stratification is done, you have a subset of the labeled data, but you only have the labeled data, so you'll have to collect more raw data and generate features by joining with the snapshots data frame that the snapshot infrastructure team provides. And after that is done, features are generated, they're fed to a model, we train the model, and then metrics are computed. The model is effectively tested based on several ranking metrics and AUC, all kind of metrics that were discussed in the earlier talk as well. And then it tends to be an iterative loop, right? And once a certain degree of confidence is reached, we go to an A/B test. So the two places where stratification is applied. One in the infrastructure component, when if we choose to snapshot all the users, it's not usually cost effective, even though we are tending to go in that direction. So we have tended to do stratification when selecting the subset of users to create snapshots data for. And similarly, during model training, if we have a lot of label data coming in corresponding to the place from our users, and that's growing day by day. But if you used all the data, it would take a little too long for the models to train, and you don't typically have to use all the data. You only need a certain subset that's representative enough for the actual idea you're trying out. So there's stratification applied there as well. So what exactly is data stratification, right? It's basically a mechanism to downsample data sets while meeting a desired distribution. So in Spark data frames, when you use the command .sample, you're creating a uniform random sample of the entire data frame without really paying attention to any conditions on what you want to sample. So stratification takes it one step further. The API allows for users to specify a lot of different rules and constraints, which I'll be talking later. Data stratification, as I mentioned earlier, is used to place constraints during the snapshot phase. And that is mostly done to reduce costs for snapshot storage and also the amount of time it would take to snapshot users. So that's done more as a sort of a convenient step in our infrastructure. Similarly, there's stratification done on the training data to make sure that models train fast, to make sure that you can iterate over those models. Hyperparameter tuning and all that stuff requires the pipeline to be quite rapid. And stratification is one of the key techniques that is used there. So what are the different criteria that we stratify our users based on? I'm going to mention a few here, but this list is growing by the day, right? So we're doing, Netflix has traditionally been a very US-heavy sort of company, but we are moving towards smaller countries. We have new emerging markets and other places in the world, and we have a lot of new users who are signing up. So over a period of time, we need our model to adapt to these changing environments as well. So we try to stratify to make sure that we have enough representation from some of these previously underrepresented demographics. And the Stratification API allows for us to specify how much to pick from each of those subsets. So here's sort of a flexible data frame stratification API that I was going to show a snippet of. The rest of my talk will talk about a specialized instance of it that we built for our snapshots infrastructure. So think of an extended method on a data frame, which could be implemented, example, via an implicit in Scala, as think of a stratify method that takes in a bunch of rules, right? So for example, the first rule there says, also let's assume that the data frame has 3 different columns: country, tenure, and place. The first rule in there says, I want to make sure that I get a subset of rows from the data frame, meeting the condition that the number of rows that have column country as US should at most be 8% of the resultant subset that I stratify from the data frame. So all that is encoded in that simple line that just says country equal to US, max %, 8.0, right? Similarly, the next rule says, apart from meeting the previous condition, I also want to make sure that the subset of the data frame that I stratify also has tenure greater than 0 and number of plays greater than 0. These are the values in the columns. And I want to make sure that there's at least 0.5% of rows satisfying that condition, right? So this is a generalized, not really type-safe sort of API on a data frame that can have arbitrary set of columns. Our initial use case was to do it on our user data frames that essentially stores metadata about all the Netflix users. So for that specialized use case, we built a Scala and a Spark domain-specific language, DSL, with strong type safety. The main goal was for it to have a lot of expressive power to build arbitrary user sets on demand, and that was primarily used by the snapshots infrastructure. The other goal was to make sure that the API was declarative enough. It only lets you inform the library what to do, but not provide too many details of how to do it. The previous API that I showed is as close to declarative as we have gotten with the Stratification API. The Netflix user base that's stored in a separate that's stored in S3 supports a lot of user attributes that you can stratify by. So currently, our list is country, tenure, number of plays that the user has made, number of searches, and this is a list that can continue to grow. As we continue to grow this list, we also keep updating the Spark and Scala DSL to match with those queries. So here's a sort of a brief architecture of how things are placed. So we have a user stratification client that's part of the Boson library that I talked about earlier. It's all completely powered by Spark, written in Scala. The user specifies a set of sampling rules via the DSL. The client reads the data from a denormalized data set that's constantly populated as part of our snapshots infrastructure. The denormalized data set, think of it as something that loads the data frame, has all the columns that you want to stratify by, and then the rules that you specify as part of the API will be satisfied by the user stratification client. So let's consider some of the key building blocks that are part of the DSL. Country.us, for example, is a case object, which is a specialized object as part of a case class called country. And we also refer to it sometimes as a user segment. This is essentially the subset of all the data in the user base whose country is US. So that can be simply referred to by country.us. And you can mix and match some of these segments. You can compose them with AND conditions and OR conditions. So this is an example of an AND condition, right? Country.us and tenure month 1. So get me all the users who belong to country US, but are also within the first month of membership. So note that this is a subset of that circle in the Venn diagram. And when you compose conditions like this, the API automatically knows which subset to look at. Similarly, another condition built with an OR condition, tenure.m1 or place for the user lying between 1 to 10. And typically, all our data sets are partitioned by date int. So when I say place 1 to 10, it refers to the number of plays made by the user on a given date, which could be between 1 and 10 plays. So this particular segment intersects with both of the previous ones. Just another example with a not condition. So all users, all international users, and also users who are within the first 10 and 100 days of tenureship. So given these building blocks, you can use the specialized stratification library to gather a smaller portion of the user set. For example, this API is showing that I'm asking for a user set that's essentially a Spark data frame that's returned by the API with the following rules satisfied, right? So for each of those 4 segments, I want to make sure that I achieve a certain count. For the first rule here, it says that I want to make sure that the number of rows in the resultant data frame is roughly about 500 in the sample data set. And I don't want anything more or anything less. Sampling automatically usually tends to be approximate. So try to meet the target of 500 as much as possible is what that declarative API says there. And similarly, the rules for the other guys. Min count says, get me at least 200, but I don't care if you exceed 200. Similarly, max count means get me at most 200. I don't want anything more than 200. That satisfies the 4th rule. A slight variation on this is the counts can also be replaced by percentages. So usually in this case, the researcher is mostly interested in ensuring that the resultant data frame has a certain distribution, but doesn't really care much about the size of the data set. And when this is the case, the API tends to maximize the size of the data set that can meet all these distribution rules. We've also added some other sort of syntactic sugar to the API. In this particular case, the second rule says country.each and tenure M2. And what that internally translates to is we do a sort of a pass over the entire original data frame, find out all the distinct countries within it, and expand that rule into a bunch of different rules where country.each is replaced by each country, right? And we do this combinatorially too. So you could have said country.each and tenure.each, in which case it'll explode all possible combinations of that. It makes it easy to concisely write your sampling rules if you don't want to go specify all possible countries or all possible categorical values of some other columns, like tenure, other stuff. So with sampling and when trying to meet a set of rules, it's sometimes your yield can be low because just because you're trying to satisfy the condition for one of the rules, which could be very strict to meet, the yield of your resultant data set can be quite low. And one way to increase that is with a parameter that says allowed error margin. So what this says is, I like to keep all those original rules, but you can be off by about 20% for each of them, right? So what that means here is, in the case of tenure month 1, I want my target percent to be between approximately 8% to 12%. So I just want to be in that range. And when you slightly relax the rules like that, it's possible to get a much larger subset. And this allows our researchers, for example, to train a bigger model while keeping the original distribution more or less intact. So just a note on the algorithm complexity. A lot of it is done on the Spark data frames. We do use this data frame .sample as the underlying key technique for satisfying each of those rules. In terms of complexity, when in the Venn diagram, if there are no overlaps between the regions, and each region is essentially a sampling rule that you're specifying, right? So if you have a certain rule, it matches a certain subset of the data frame. And if all your rules are non-overlapping in that imaginary Venn space, it's actually quite trivial for us to go and determine how much fraction we should be sampling from each of those individual segments. And that turns out to be a closed expression, and it can be done easily in the code. But when the regions overlap, the problem tends to be much more complex. We had to formulate this optimization problem as a linear programming problem. The sampling rules form the constraints for the linear programming problem, and the default objective is to maximize the sample size. But the objective is configurable, and any API invocation can have a different objective to meet. But that's currently not implemented. It's a possible extension. So to give you an example, let's take the case of two simple regions. Each region corresponds to a sampling rule. So in this case, let's assume that for the circle that's titled C1, let's assume that the original count in that yellow circle is C1 minus what's there in the overlap region. And let's assume what's there in the overlap region is C12, and C2 is the count of the number of rows in the data frame that satisfy the other region. So if the condition on these two regions is C1, for the region C1, I want to make sure that the min percentage is P1, and similarly for the other one, min percentage P2. It can be translated to a linear programming formulation where you specify all the constraints, right? So in this case, S1 is the amount that you're trying to sample from the region corresponding to C1. And the simple constraint is S1 must lie between 0 and C1. S2 must lie between 0 and C2. And similarly for S12, which is the amount that you want to sample from the overlap region. The other constraint, in fact, the more important constraint that needs to be satisfied is S1 plus S12, which is the total amount that you're sampling from the yellow region in the graph, should be at least P1 percentage greater than the original counts. And similarly for the other guy. So So this is a simple example for two regions that happen to overlap. When you have n regions which overlap m times, you have a lot more rules and combinations like that. So, and the complexity is directly proportional to the number of overlap regions. So if all your regions are overlapping in a very heavy way, it does get a little tenuous, but in most of our use cases, that tends to be not the case. A shout out to the third-party idiomatic Scala library that I use for linear programming. It's called Optimist. It's written in a pretty idiomatic way that all it took was a few lines like that I'm showing in the slide to implement the entire linear programming formulation. So a for each loop that goes over each of those regions, and within each of those regions, we can apply those constraints that I was mentioning in the previous slide. So this also made it much easier to code, test, and fit into our Spark and Scala ecosystem pretty well. Cool. That's it.
Great talk, thank you. I was curious on two things. First, a quick question, is that Optimus library, what is the license like? And the second question is, maybe I was confused on the linear program, but how do you prevent the program from not choosing the entire, if you maximize, how do you prevent it from choosing the entire data set? That's a bit that I didn't quite catch. Thank you.
So the first question is Optimus Apache license? Yes. That's true. And the second question is, for the linear programming problem, how do we look at the entire data set and satisfy all the rules?
Yeah, so you can, if you pick maybe the entire data set, you satisfy all the constraints, right? But you somehow need to reduce the sample. How do you express that reduction in the linear program?
Okay. Not sure I quite get the question, but maybe we can take it offline. So just a note on the linear programming formulation itself. That's completely implemented in the Spark driver. The implementation and the engine that runs the LP formulation is not distributed to the executors. It's not a distributed algorithm. So what we do is we compute the statistics of the underlying data frame. So unfortunately, we'll have to go through one or two passes of the original data set. Looks like that's what you wanted to get at. So in that case, it is slightly different from the regular sample that you see in data frames. That is completely lazy. We'll have to give up on that a little bit. But in many of our use cases, we try to cut the lineage. We use dot persist, and so that multiple passes over the data frame isn't prohibitive.
Does the API allow upsampling? And in case of upsampling, your optimization problem becomes really easy. And also, if a particular data scientist doesn't care about, if it's okay for them to upsample, does the API allow upsampling?
I just request the next questioner to come to maybe talk a little louder.
Okay,
maybe
sure.
From here, I'm not able to hear the question. Yeah.
The question was, does the API allow upsampling? And follow-up is, if so, the optimization problem would become easier. So that is just a guess. So the first question is, does it allow upsampling? And second thing is, my guess is that, in your opinion, correct?
Okay. The first question is, does the API allow upsampling? No, it doesn't, fortunately. So data stratification is all about taking the actual backing big data set and downsample it to a point where that's manageable for our model training pipeline. So it doesn't allow upsampling at this point.
Yeah, if we want to use this, is the Stratify library available in open source? And then what does it do when it cannot satisfy the rules?
Yeah, yes, there are plans to open source it. I'm not sure about the timeline. Maybe you can talk offline and I can give you some indicators on that. But yes, there are definite plans to open source it. I might start off with a third-party library with extending Spark data frames using implicit definitions and take it from there.
Okay, thanks.